So that's the title of my talk. But maybe if you are not particularly, oh, why is it auto-playing? Particularly interested in stream operators or streams, just there's a more general idea in here of expressing business logic declaratively. So maybe just follow that if streams are not your thing. Now, when I say a stream operator, this is the image that I have in my head. A box with some input streams and some output streams, and inside is business logic. Now, by safe, I mean that many wrong programs are prevented before execution. And by simple, I just mean that there's low non-essential complexity. What's a stream anyway? Let's just work with the intuitive definition of a sequence of elements that's produced and consumed gradually. And we can then distinguish whether the stream is proactively producing elements and pushing them to the consumer, or it is reacting to consumer demand. Of the first kind are, for example, publisher from reactive streams or Akka source, and of the second kind are FS2 streams or ZIO streams. And for completeness, we could approach. Oh, and that's where we will spend our time today, mostly with Libretto's source. But we could approach streaming from the consumer perspective, working with things and such, and we might get to that if we have time. Existing libraries come usually with a lot of built-in operators that you can compose nicely. It's a pleasure to work with usually and can get us quite far. But what if we really need something custom? The story then usually is that you have to leave the nice world of declarative concurrency and enter iterative programming with things like queues, mutable state, promises, fibers, synchronization primitives, resource scopes, interactions, and so on. And your business logic gets lost in all this accidental complexity. It then becomes hard to answer questions about your code, like, am I completing all the promises? Am I not trying to complete a promise twice? Or am I not losing elements? Is this state that I thought was unreachable really unreachable? Am I not attempting to pull from a closed source or queue? What about updating mutable variables? Will the other side notice my update? What about cancellation? When fibers get canceled? Oh, is the resource that I'm using still alive? And so on and so forth. Sorry for that. Yeah, got it. Yes. And this I find neither safe nor simple, and frankly, this is not what I signed up for when I got into functional programming. So I'll now work out a few examples using Libretto and hopefully convince you that we can regain safety, stay focused on business logic, and that Libretto delivers on the promise of declarative concurrency. Our first example will be packaging doc presents. We have input streams with doc toys, bones, which are either large or small, and doc biscuits. And on the output, we want wrapped presents. Each present will contain one toy, one bone, and if it's large, we add 3 biscuits. If it's only a small bone, we add 5 biscuits. Now, what makes this example somewhat interesting is the fact that the pulling behavior from the biscuit stream depends on the value previously pulled from the bone stream. Let's first solve this example visually. We start with an empty box and input streams at the top, output streams at the bottom, and in blue are things that still have to be consumed, and in yellow are things that still have to be produced. This Libretto source, as I said, is driven by the consumer. So we will wait for consumer action, whether they close the source or want the next element. And this consumer choice literally is the definition of source in Libretto. So we have just expanded the definition and now reduce the obligation to produce the source to an obligation to produce this consumer choice. To produce this consumer choice, we have to handle both options. And what we have done here is we inserted a piece that filled in the hole fully, but has two new holes inside. Can now clear this from the screen so to reclaim some working memory. And on the left is the case when the downstream is closing, in which case we close all the input sources concurrently and wait for all the closing operations to complete. On the right, the downstream is pulling. So we start pulling the sources. Let's start with the toy. We try to obtain a toy, but it might result in end of the stream, or we successfully got a toy and the rest of the inputs. So we are now going to branch based on this result, but first then let's bring these other unconsumed inputs into each of those branches, and there's an operator for that. And now we branch. On the left is the case when there's no more toys, so we close the remaining inputs as before, wait for all operations to complete, and return an empty result. On the right, we now successfully obtained one toy, so we're going to try to get a bone. And let's skip ahead and suppose we got it. We now classify its size, whether large or small, and going to branch based on the result. So we again distribute the other inputs into each branch, and then branch. Now the cases with small and large bone are going to be analogous, so let's focus on one. We are now going to try to obtain 3 biscuits from this biscuit source. Let's again assume that we succeeded. In this case, we know we will be emitting a present. So we do. We wrap the items into a present and are now left with the hole where we have to produce the rest of the presents from the tails of the input sources. Now the signature of this hole is the same as the signature of our hole operator, and we fill it in using recursion. And we are now done. All ports have been connected, and the way the pieces fit together is such that you cannot connect a port twice. Now, why I went through this exercise of going through it visually is because Libretto's internal representation corresponds quite closely to these diagrams. We now just need some DSL to write descriptions of these diagrams in Scala. So that's what we do next. Let's not focus on the syntactic details too much. We'll stick to our convention of marking unconsumed things in blue and consumed things and things to produced in yellow. And this lollipop arrow is the data structure that represents our well-wired diagrams. We have support for constructing recursive diagrams, and we produce a source by handling both consumer options. And these lambdas lets us use familiar Scala anonymous function syntax to wire up the unconnected ports of the diagram. In the case the downstream is closing, as on the diagram, we close all the input sources and wait for the operations to complete. If the downstream is asking for the next item, we start polling. We start with toys. Suppose we successfully got a toy. In that case, we proceed with obtaining a bone. Again, let's suppose we succeeded. We classify its size. Suppose it's large. Try to obtain 3 biscuits. If we succeeded, we will now be wrapping a present and calling ourselves recursively to complete wiring up the diagram. Now, in the case we didn't obtain all the biscuits, notice here how we have to explicitly discard the items that we have pulled previously. Otherwise, that would not be a well-wired diagram. So this is now a well-wired diagram, but let's break it in that way, that we, for example, forgot to handle something. We would be like losing this item, or that we would attempt to close an already closed source. These are not well-wired diagrams. So then what happens if I write this code, though? It has to break somewhere, and where it breaks is on the surrounding lambda, which was on the previous slide. The lambda tries to assemble the diagram description from this Scala code, but if badly wired diagrams are not even representable, then it throws an exception. And I call it an assembly time error, which is before execution, which is before we even obtain the blueprint for execution. And to guard us against these badly wired diagrams, this one-line test suffices to catch those violations. Now, what would be our alternative fit without Libretto? And with this example, I can imagine the closest I can imagine is FS2 conversion of a stream to pool, where then you can handle pull elements one by one and do some business logic and flat map and do the rest, or somewhat similar ZIO streams to pull as well, but it's somewhat more complexity, and you don't get any of the well-wiring guarantees that you get with Libretto. And this gap between Libretto and other tools only gets bigger with other examples I will show. Now let me quickly show that how to use these Libretto operators with ZIO streams. So we would have we would want to have a function with our input streams as ZIO streams and produce a ZIO stream as output running within some scope. And let's not go into the details. Let's just say it's doable in these 3 lines of code. Moving on to our next example, we'll be processing sunflowers to produce either bottles of oil or roasted sunflower seeds. We'll need 5 sunflowers to produce a bottle of oil, or 3 sunflowers to produce a pack of roasted seeds. Now the consumers will be competing, and whichever pulls first gets access to the source and fetches 3 or 5 consecutive sunflowers and produces the item. Now what makes this interesting is exactly this non-deterministic racing behavior of the consumers that's driving the behavior of the operator. Now you might start thinking how you would implement that. You could say, oh, let's feed the source into a queue and let the consumers run each in its own fiber and let them compete for the queue. But we want to pull 3 or 5 consecutive fibers, so maybe add a lock to protect access to the queue. And but then we need to notify the upstreams once both consumers close, that the upstreams should close as well. So perhaps use a countdown ledge for that. And all of these things like queue, fiber, lock, countdown ledge are liabilities that you need to manage carefully in your code. But thankfully, none of that is needed with Libretto. So let's do the Libretto version. We name our input using the lambda that we saw before, and we name our outputs using this producing function, which is like the lambda, except we are naming the outputs. Now we are going to branch based on which consumer acted first, and this output sources are able each to give us a notification that they acted, and we'll raise those notifications using this select by operator. Again, don't focus too much on the specifics of the syntax, and we can then test whether which consumer acted first. Let's suppose it was the left one, the seeds output. We check whether it is closing or asking for the next item. If it was asking for the next item, we try to pull 3 sunflowers, and if we succeed, we roast the seeds to produce 1 pack of roasted seeds, and call ourselves recursively to produce the rest of the outputs. Now, our task here is to connect those, to fulfill those yellow variables using the blue ones. And if the types match, we can do so using these assignment operators. And now the first and second part of the output matches those unconsumed expressions. And we now have a well-wired diagrams. We did not use any imperative constructs like the queue or lock. And the operator might look stateful from the outside. It clearly has some state, but we didn't use any mutable state, any mutable variables here. Just follow the business logic and branch based on the business logic. This is our final example, digital library of Alexandria. We are given an API to the library where if we give an ID of papyrus scroll, you would get it back in a digital form in scanned pages. The thing, though, is that not all of it has been scanned before, so your request might trigger a robot to go fetch the scroll and scan it and only then transfer the data. So there would be a long waiting time before the data transfer starts, and the data transfer is then quite fast. and by their fair use policy, we are only allowed some small number, k, of concurrent connections. And our task is we get a source of scroll IDs as input and want to output all the scanned documents concatenated in the given order. And we want to maximize the use of all allowed connections. So what we are going for is start all k concurrent connections immediately to start preparing k documents. As soon as the first one is transferred, start transferring the second one, but also open the k plus first connection to start preparing the next document, and so on. And what makes this example interesting are those lifetimes of the connections that are not easily mapped to nested scopes of some other libraries like FS2 or getEffect or ZIO. And I'm not sure the supervisor that we saw today makes this much easier, but let me know. So suppose we are given this function that takes a scroll ID and the connector and returns a source of pages. And given that, we want to construct our operator that fetches all the given scrolls using the connector. So we map the input source for each scroll ID called the fetch scroll function, which gives us a source of sources. We do prefetch on this source of sources to prepare the documents ahead before they will eventually be downloaded. Notice that if the prefetched elements are not actually downloaded, then they have to be consumed somehow. So here we provide a handler for that. And then we just flatten the resulting source of sources to obtain our flat source of pages. And this is a correct and resource-safe solution in Libretto. This will probably be surprising if you have experience with, say, FS2 streams, because this solution does not translate to libraries like FS2 or ZIO Stream, where the stream type is a blueprint. Let me quickly say why. Because if we did the same thing, if we did prefetch on a stream of streams, we are prefetching these blueprints. This stream is just the blueprint, so it doesn't start preparing anything on the backend, and that's not what we wanted. If we flip the operations, first flatten, then we are prefetching just the individual pages, which is also not what we wanted. We might try to use this map async method for each scroll ID to do some effect that, for example, open that connection and start preparing the document. But then that connection has to be closed at some point, and we would like it to be closed at the end of the stream. But you know, the stream is a wannabe blueprint, so it doesn't even has to be consumed. So this is not resource safe. And I don't know of a simple and safe solution to this problem with alternative libraries, but I'm open to suggestions. So then, why does it work with Libretto in the first place? So first, source is not a blueprint. It's a type that describes an interface of interaction. That is, it has these two actions, pull or close. And there are running processes on each side of the interface. and the running process inside here would be opening a connection and start to prepare the document. And the other important ingredient is that we cannot simply ignore things. There's linearity. You have to explicitly close things. So you cannot ignore this output source. If you are closing it, it has to translate to closing the inner sources, which will have to translate to closing the connection. And so it is all resource safe, and the description is declarative. I would say it's this. It can be reduced to this one line up here, and so hopefully this convinces you that we got a declarative concurrency here. So my conclusion is simple. The general takeaway is that we can have a DSL that is both declarative and expressive at the same time. And more specifically, that stream operators written in Libretto are safer and simpler than the alternatives. Now, I know this is a strong claim, and I might be biased, so feel free to challenge my conclusions, ideally with simple and safe solutions to the presented examples, or bring your own examples to test the limits of Libretto. And how are we doing with them? I have a couple bonus slides, but maybe it's a good time to open to questions, if there are any.
Okay, thank you, Tomas. Do we have a question, maybe?
Thank you for the talk. Given that the whole process is declarative, you have some sort of way to visualize that? Did you already build something like this? Or is it
that's a great question.
theoretical?
I haven't, but all those diagrams I was showing, it will be possible to generate them from code, yes. That's something I would like to have, and that is possible because it's not like with I/O where your program is hidden after the first flat map behind some opaque Scala function, but you really see the structure of the program. So that's definitely something I would like to have, and is possible.
Okay. I would also like to add that your usage of like the switch expression, like the way that you do pattern matching, but not really, because it's based on still a declarative way to do things, not actually pattern matching on the elements. It inspires me because I had some similar issue when trying to design something.
So that is some auxiliary syntax to help the wiring, but then it constructs some expression that is then taken by the lambda that works its way back then to construct those diagrams. So there is some processing there, and it happens in that assembly time that I mentioned.
Okay, do we have one more question? Yeah, in the middle, okay.
Thanks. How would you describe the growth factor of each diagram that is created? Like, for instance, let's imagine we've got this dog packaging, these packages, and we add apart from toy, bones, and biscuits, we add some yet another toy that might be completely different from the first one. And how would you describe the growth factor of the diagram?
I'm not sure I understand what you mean. Do you mean something like how, a complexity, like computational complexity, or how big it could get, or something like that? Or what do you mean by growth factor?
Let's say maybe the complexity, how much, let's say how much lines of code probably, or would you add to it? How many, or in the terms of the possible yet another switches.
Well, so I showed, so with the first example, I showed the diagram, and then I showed the real code for it. So it corresponds up to some constant factor, right? Like the amount of code and like amount of elements on the diagram, right? But I'm not sure that's what you are getting at, or it's not like there would be a simple diagram and then some like exponential explosion of code corresponding to the diagram.